Okay, this is a bad sketch of, parabola is really not a parabola. It's got a bit of a kink right there. But a ball rolls off or out to the floor, and at some angle, let's just say we're going to do this for 30 degrees. We find that the ball maximized the distance, okay? But we found that. We seem to have found that around 30 degrees. All right. Let's just generalize the situation where our angle is theta. This is a 60 centimeter ramp. Distance to the floor is approximately 1 meter. And whatever distance you observe, again, appears to have been maximized around 30 degrees for everybody. And the tables were of different height. Does that make a difference? Okay, so you got angle theta. I'm going to say path length L. I'll use a capital L, although I'd much rather use a small script L, just because of the way I have to type it. Small script L looks like a 1, that causes confusion. So we got this path length L, and we've got a drop height H. And we want to find at what angle the distance is maximized, the horizontal range is maximized. Okay. First of all, we know the angle, so we know the initial angle of the projectile. If we know L, we can figure out how fast the ball is rolling, right? Okay, that makes sense. Okay, so we want to write an expression and I don't think I want to use X, because I'm going to use that on the ramp as well as the projectile. So there's a horizontal range to be R. One expression for the horizontal range in terms of L, H, theta, and a ramp, which is acceleration on the ramp. Now we just observed that the acceleration of a ball on one of these groove tracks is not the acceleration we would expect if the only forces were gravity, normal force, so that the accelerating force is the component of gravitational force parallel to the ramp. And we worked on that last week, so we should understand the free body diagram and so forth. it turns out that the rolling friction of the ball is very low, but some of the energy that the ball gains from moving lower on the ramp, and we haven't talked about energy, just take my word for it. Some of that energy goes into rotating the ball. Now, if we accelerate a cart on a low friction ramp, or even better, and I don't want to pull out the air tracks, but even better, a glider on an air track, okay, we can release this cart, and the acceleration is going to be pretty close. And the net force is going to be pretty close to the component of the gravitational force parallel to the ramp. Okay. And we brace the two components with the track and the cart track and the ball track at the same angle. And we found that when the cart goes approximately 2 feet, 60 centimeters, it ends up a cart length ahead of the ball. And the length of the cart is about 16 centimeters. In 60 centimeters, the cart beat the ball. Okay, as the cart moved 60 centimeters, the ball only moved about 40. Okay. And we assume that the acceleration was uniform. It's a pretty good assumption. Well, that's our situation. We want to write an expression for horizontal range in terms of 1, 2, 3, 4 variables. So in terms of L, theta, and A ramp, acceleration on the ramp, ball's velocity is the instant it leaves the ramp. Now, just to be sure you understand the situation, go ahead and write it out for some numbers. Write it out for the distance you think the ball traveled, which would be a little less than 60 centimeters. Go ahead and call it 60 centimeters. Okay. Go ahead and use angle 30 degrees and assume the acceleration on the ramp acceleration of the ramp will be g sine theta. Take just a couple of minutes and outline how you would solve the problem. What equation would you use? How would you use them? And how would you determine the velocity of the ball at the end of the ramp? Okay. Some people are making progress and some people are still at the starting gate. Can't wait. Okay. You need to get out of the starting gate. Okay. Well, I'd say we could use the equation bf squared equals v naught squared plus 2a. I'm just going to use delta x for x minus x naught. Okay. And that could just be f if you assume x naught is 0. So you can set it up as you wish, but what do we know? We know the initial velocity, we know the acceleration, and we know delta x. So we can very easily find velocity. So this equals, this is 0, as we're starting from rest. And this is 2g sine theta times, I'll go ahead and use delta x. So we're going to discard the minus case. So there's your velocity, okay? Okay, so now you've got that. Now, that's what you get with symbols, okay? You don't have to use numbers. You don't have to worry about conversions until you get to the end of the problem. So now we have an expression for the velocity at the end of the graph, okay? So and when I said delta x, that was kind of a mistake, because I said do this in terms of L theta A ramp, okay? So I shouldn't use delta x here, I should use L. All right, well, you plug your numbers in, okay? If you use theta equals 30 degrees, the sine of 30 degrees, everybody knows that, right? It's 1/2. On the equilateral triangle, cut it in half, and you got a 30-60 triangle. And this is, if this is 1, this is 2, this is the square root of 3. So that the sine of this is, if this is the angle, opposite over hypotenuse is 1/2. Cosine is square root of 3 over 2, which is about 0.87. You got to know those. You can't live as an engineer without knowing those. Can't think as an engineer. You're not thinking if you're punching things into a calculator. You're just getting an answer, okay? If you do it with symbols, then you're thinking and you're doing it, okay? Now, it's okay if you know what to put into the calculator. That's good, okay? If you know why you're putting it into the calculator and know what it all means, it's much better, okay? So bottom line, know what to put into the calculator, but also be able to do this. So if sine theta is 1/2, that takes care of the 2 here. You got G times L, okay? And L is 0.6 meters, and G is 10 meters per second squared approximately, so it's square root of 6, which is about 2.45 or something like that. Pretty close to 2.45. Okay. So for calculate that. And you didn't have to write down any units or anything until you got this expression because you derived it. And the derivation is really, really simple if you know this formula. Okay. Even better if you can derive this formula starting with uniform acceleration, integrating, or other arguments. Okay, well, there we have. Okay, so there's your velocity at this point. Well, now you got a projectile. How far is the projectile going to go? Did you measure how far the projectile went? Yeah, either yes or no. You know, you might have, you might not have. I didn't tell you to, but You want to observe everything that's going on in any setup. So you should observe everything, whether I tell you to or not, right? You might not think of everything. That would be pretty obvious. I hope you think of it. If you didn't, we'll live. Because you're mainly looking for the angle at which you have the maximum. Okay. And that gets a lot hairier than any of this. It gets really hairy. Gets to an equation I don't think can be solved. Okay. Well, now we have the projectile. Okay, V naught's this, theta is 30 degrees below horizontal. Okay. But you have to use theta because we're going to change it. I'm going to ask what should be the horizontal range for this theta, for that theta, whatever. We want a formula that we can plug our numbers into. So we can set it up in Excel or some algebra program and get a bunch of answers, get a curve that tells us where the maximum is, because I don't think we're going to be able to do it using calculus. We're going to try. We're going to get the expression and we're going to try to maximize it. Okay. We're going to try to maximize it for theta. So that means we're going to take the derivative with respect to theta, see if we can figure out when it's zero. That ought to tell us where the maximum is. Okay. It's very simple, except the derivative is a little hairy. And the equation you got to solve to set that equal to zero, you can't solve. I don't think I can solve it. I don't think anybody can solve it. I think you just about have to draw the curve and see where the top is. Okay. But I haven't tried. Really, I just looked at it and said, man, I don't want to solve that. I don't think it can be solved. You got a sine theta out here, and then you got sine thetas under a radical in the denominator. And even you put everything over a numerator, you got terms that just aren't going to reconcile, but maybe they do. I just haven't tried. I didn't have time to look at it much. I went ahead and drive it. Said, okay, can I ask people to do this? And they said, yeah, I'm going. All right. Okay, so here we have it. Okay, so there you have theta. So what are V naught Y and V naught X? Okay, so people did okay with this. They had the right idea, but they didn't do exactly what I asked. So understand what I asked. I mean, it's simple. You had what I hoped you'd have. Actually, I hope you have a negative sign where you need one if nobody did. That's easy to understand. Okay, so the essential thing is that V naught X equals V naught cosine theta, right? And if that's all you wrote down, that's good. But V naught is this. So, and you need this square root of 2g sine theta times L. I'm going to start writing that as 2gl sine theta because you don't want to maybe use a chain rule on a theta L or something like that. Okay. Well, it's negative V naught sine theta. And I didn't have my V naught on the V naught X. There it is. Probably erase that, try to write it a little better, but it's negative V naught times the square root of 2gl I'm so busy saying things that I'm not thinking. Let me say it clearly, because that was about as clear as mine. V naught x, you know what it is, equals V naught cosine theta, which I'm going to write now is square root of 2GL sine theta times cosine theta. V naught y is negative V naught sine theta equals negative square root of 2GL sine theta times sine of theta. All right, so now it's really easy. Just plug all that in to your analysis of the motion. Okay. Well, if you've done a few projectile problems, you know that the next thing you want to do, let me make sure it's on the screen. Next thing you want to do, and where does the screen start? It's about here. Give me a second. Good. Yeah. Okay. So next thing you want to do with the projectile problem is you want to analyze the vertical motion. That'll tell you the time to fall. Okay. You know your delta y, your v naught y, and your acceleration is just negative 2, right? You find t, and then just multiply v naught x by t, and you find out your horizontal range. It's the simplest possible projectile problem where you have an A. Okay. Now, if you got numbers, it's pretty easy because your equation for t in terms of these things is quadratic. Okay, you can't escape it. Okay, you can't escape the quadratic. You could either find final velocity using the VF squared, you know, and so forth. Okay, V naught squared 2A delta y. Or you can solve the delta x equals V naught t plus 1/2 AT squared for t. It's a quadratic. Okay. If you use VF squared, you're going to get a square root. Okay. If you use a quadratic, you're going to get a square root. And you're going to be stuck with square roots of complicated, relatively complicated expressions. You can't avoid it. So we'll just go ahead and bite the bullet and use subscript y on the acceleration there. And of course, we're going to use that in the form delta y is, H is another parameter. I listed it here. I didn't list it here. I want to do this in terms of these parameters. I'm going to do this in terms of H. So your delta y is negative H. Well, write out what your equation is. I'm not going to write it out all for you. Want you to understand that this isn't really as bad as it looks. You just write out what you need to write out. Okay, so most did pretty well, but remember, we want to do things in terms of H, L, beta, and A ramp. Okay, now actually we don't need A ramp because we're assuming A ramp is G sine theta. Okay, and really I probably should have used A ramp instead of G sine theta, but I want you to see it's going to be a multiple of G sine theta because of the angular momentum sucking out, or the angular motion sucking out some of the energy. Nice. We'll get that in the chapter following the one we're going to start this week. Okay, so we've got negative H equals V naught Y. V naught Y was this. We look back, we check, if we good engineering and check and say, does that make sense? Yeah, that makes sense. Do the units work out? Dimensional analysis of GL, that's meters squared over second squared. The square root of that would be meters per second. Yeah, dimensional, or length squared over time squared, however you want to look at it. Okay, so we get this equals V naught Y, which is negative square root of 2 GL sine theta times T minus 1/2 VT squared, because AY is G, and you should know that. Okay. I used AY up here because that's the way your equations are set up. And you don't want to always assume that AY is equal to G until you're sure there are no drag forces or whatever. Okay. Or maybe you're on a different planet. Okay, speaking of being on another planet, I didn't put my sine theta in here. It's just so much more fun if it's in there. Well, let me write it out correctly. Okay. And I'll go ahead and just erase this. Maybe I'll use a space to write something, just pretend I didn't make a mistake. But probably not, I'll just leave the mistake there. Okay, so here we have it. Okay, so it equals what? Very simple. Use a quadratic formula. Of course, you got to put the thing in the right form. Well, I know the answer to that question. Okay. My comment was, I think you're good. So let's see if I am. Okay. Anyhow, T is what? Well, if you rearrange this, I would think of bringing all these negative quantities over onto this side because you're going to want your T squared and your T term and your constant term, right? And you might even multiply through by 2 to get rid of the fraction, but it's not a difficult fraction, so we're just going to live with it. Okay, so T is going to be what? Oh, also, it's going to make your denominator simple. So T is going to be this, except going to need a negative on there. Then it'll be plus or minus the square root of square of this. And the square of this is going to be 2 GL sine theta and the sine squared of theta. So it's going to be 2 GL sine cube of theta. We agree? Look a little dubious, but well, think about it. Okay. So you got to square this. And it doesn't matter if it's plus or minus when you square it, it's going to be positive. And then it's going to be 1/2 GH. all that over G. Now something's wrong with that. I can immediately see that nothing's wrong with it. Okay. Okay. Somehow I was looking at GH and GL thinking, oh, let's have the same units. I don't know what I'm thinking because it's acceleration times distance, acceleration times distance gives you length squared over time squared, which is length over time. And you divide that by G, which is length over time squared. Okay. And you get time. And this one is going to be length over time. Yeah, divided by length over time squared gives you time. So the units are all consistent. So there's at least an outside possibility that I've written this down correctly. Okay. So there's T. It's not that complicated. You just got to keep your wits about you. Be careful of your bookkeeping like I'm not. Okay. But then do your dimensional analysis and then trace back to your steps to make sure you've got it right, because you're going to be pretty well committed to this thing when you start doing calculus with it. Okay. Just got to maximize our horizontal range. Okay, so now it says V naught xt because you got zero acceleration in the horizontal direction. And again, you should be well versed with that. Okay. So you just write this down times T. But this times, this is T. You write this down times V naught x. And V naught x is square root of. Okay, I'm going to need more room. It's your final velocity of the ramp times the cosine of theta times T. Well, that equals okay, I gotta get rid of this. Platform. I'm not going to write it up. Okay. It's easy to write out. I'm going to let you write it out. This is 5-minute exercise for homework. Make sure you got it written out next time. Okay. Okay, about to see if, I don't know if this is your first partial derivative. I'll bet you saw some partial derivatives in differential equations, did you? If you did, you might not even remember because it wouldn't have been required. Okay. I don't know if Jason chose to look at a little bit of partial differential equations or not. You can do a little of that. Sometimes I do when I teach the course, but usually I don't. So I know I think sometimes he thinks about doing it, but doesn't always have the opportunity. Okay, so consider R as a function of what? Well, L, theta, H. For this time, we don't actually leave it off. We're using the ideal G sine theta for A ramp, okay? If we find that the acceleration is, let's say, 0.8 times G, then we just throw a 0.8 in here where we have G, okay? Nothing to it. And then we're gonna have G's up here too, but we'll have 0.8s. And it's gonna change some of the derivatives, but only by a constant term. And if you do the derivatives, you're okay. Okay, so well. We write R not as a function of L, not as a function of theta, not as a function of H, but as a function of all three. Now, if you want to graph that, you're out of luck. You graph a function of three variables, you need 4 dimensions, just like you need 2 dimensions to graph a function of 1 variable. You need 1 more dimension, then you got variables, and you wimps can't visualize 4 dimensions. Well, nobody can. Okay, so you're not really wimps. Okay. So we write this equals and write out what you get. Okay. But now, for the moment, L and H be fixed. Okay. So now R is just a function of theta. So you've got your experimental setup where you're always rolling the ball down, same distance down the ramp, but you're changing theta. And the height of the end of the ramp remains at the edge of the table, so it doesn't change. Okay. So we're confining our attention just to the variation with theta. Doesn't mean we can't do the variation with L and the variation with H, and even a differential of the whole function. I'm probably going to write that out for you just so you take the idea of a differential seriously. Okay. But there you have it, just as a function of theta. What R of theta just for now. Okay. So what you want to do and what I want you to do for next time is a simple exercise in calculus. Messy, but very simple. Okay. It's so messy that you might screw up the rules. That doesn't mean it's not simple. That means you just got to be really careful and know what the rules are. Okay. Presumably you do. But you know, you're going to have to use chain rule and stuff. Okay. And it's messy. So any individual's chance of getting it right on the first try are not all that high, just depending on how careful you are. Okay. There are plenty of opportunities to screw something up. So be good engineers and see if you can do it without screwing up. If you do, I'll be impressed. Okay. I'll write out my solution. Hope I remember to do that, but I'll write it out. Okay. But it's just simple calculus. So simply maximize our thing. Okay. How do you maximize a function? You find the critical point. How do you find the critical point? you set the derivative equal to 0. Well, there lies the road. Okay. Set d theta equal to 0 and solve it. Simple enough, right? Except, of course, your derivative is going to involve this expression and this expression. And you got thetas all over the place in both expressions, right? It's going to be a pain in the behind. I don't want you to do it just for the good it does you. Okay? You'll have to do much tougher calculations than that in engineering curriculum. Maybe you already have, but maybe not at this point. Okay? I want you to get familiar with the calculus. Now, ultimately, as engineers, you're going to use software to do all this. Okay? But if you don't understand what's going on with the calculus, you're not going to understand what the software is doing. You're just going to take the answer, cross your fingers, and hope that you got the right one. And you got ways of checking it and stuff like that. You know, engineers do that. So hang on a second. Okay, we got the question. Will you look at my R of theta and tell me if it's right? At first place, don't trust me with anything like that. Is it dimensionally correct? If it's dimensionally correct, there's a good chance that it's right. And if it's wrong, I don't care because it's easy enough to correct. You're going to use, I guess, octave would probably be the thing of choice, or Excel, depending on how you choose to set it up. But I'm going to want you to get a graph of R versus theta. Okay. And if your graph is ridiculous, as I said, then you go back and do what a good engineer or a good physicist would do, or a good anybody whose curriculum follows this course. Okay. You say, geez, let's use a little common sense. That graph has several loops in it, and a graph can't have loops in it, and it's a function. Okay. So there's something wrong with it. Well, it's probably not going to have loops in it, but, or it gives you nothing but imaginary numbers. Or it's oscillatory, which from the system, you've had your hands in the system, you know what it does. Okay. You keep increasing the angle, and for a while, the horizontal range increases. And then past a certain point, the horizontal range starts decreasing and you focus on where it was. And I think you came within a degree of the actual result. Now, the result of this thing, when you put your numbers in it, you can put your numbers in it after you get the expression, right? Okay. You put different sets of numbers in here because, you know, you can go ahead and put 58 centimeters for L if that's how far the ball is actually rolling before it rolled off the end. Okay. Doesn't hurt. You don't need to round it to 60 for the calculations to make it to be easy. Okay. Because the software is going to take care of that. Now you should run it for the numbers that you have. You should plug them in. That's just a natural thing. Okay. Plug those numbers in and see if anything makes sense. Okay. But then do the symbols so that you can treat this as a function of 3 variables and get a graph for any combination of L and H that you want. You know, roll it a little further, don't roll it as far, see if that changes where the maximum occurs. Okay, well, and you know what that is because you've done the experiment. Okay, so you set this equal to 0 and solve, but probably impossible to try anyway because it's good for your soul. Okay, good for your engineer soul to try to solve that. It's such a mess that you'll think about a way to prove that it's impossible so you don't have to do it. Okay. So you probably won't get to that point, but you know, give it a good 15 or 20 minutes. It's worth it. Okay. Um, okay. Now that is using your experimental values of L, H. Okay. And theta is your variable, so you're not going to use theta. See how well it agrees. With your conclusion. Okay. Okay, well, this is the easy problem. Okay. The hard problem is using the horizontal range that you've observed to figure out what theta ought to be. Okay. And we're not going to do that. But you can do that using the same calculus you've used here. And it's the hard projectile problem applied to this variable situation you observed in lab. Okay. And that's really too hard for most physics, so much too hard for most people to come into this class. Now, if you want to show off, you can see if you can do it, because about every third year we get somebody who can do it. Okay. Back when we had more people in class, if you have 10 people in class, there's a fairly good chance one can do it. I think in the last 10 years, I've seen a small handful, no more than, it's probably more like this, who are capable of doing it. Some of who could do it pretty easily. It's not easy for me. Okay, I just know how to do it because I know how to do it. Okay, tough problem. And it was one that confused me when I took the course. I was able to do it, but after beating several dents into the wall with my head. Okay, not literally, but it's that kind of problem. Okay, so if you want a challenging problem, want to tackle it, I'll be glad to coach you on it. Fair enough. Okay, let's see if we can get this thing to focus on the board. Yeah, let's pause it for a second. Just for a little bonus for anybody who happened to watch the video, just to see what's going to go on. Using G sine theta for A ramp is ideal. What we observed with the ball racing the cart, where the cart has very low, an acceleration very close to G sine theta. Okay, we found that the ball went about 40 centimeters while the cart went about 60 centimeters. Well, that means that the ratio of your accelerations ought to be the square root of the ratio of the distances. Okay. The ratio of the distances is 2/3. So the ratio of the accelerations ought to be the square root of 2/3. Now, the square root of 0.64 is 0.8. 2/3 is not 0.64, it's more like 0.67. So about 0.81 something. And you would throw that 0.81 something into this G sine theta. So that every place you've got a G sine theta, every term came from a G sine theta would have a 0.8. So like the 2 GL sine theta would become 2 times 0.8 GL sine theta, which would be 1.6 L sine theta. That's a very simple change. Okay. So instead of G, any G that you would have in a final expression would become a 0.8 G, 0.81 G. So we could easily accommodate the fact that we don't have the ideal acceleration from some observation of the actual acceleration of a ball on the ramp that we use. And again, I'm thinking that's probably about, it's on the ballpark, very close, I think, to 800 centimeters per second squared or 8 meters per second squared. You could even, well, there you have it. So think about that and think why the ratio of the acceleration should be the square root of the actually reciprocal ratio of the, no, I'm sorry, it would be the square root of the ratio of the distances. And also consider the possibility that what I just said was really stupid. Maybe it's the ratio of the distances. Okay, you work that out from the equations. It's very easy. And it could be that I gave you the wrong ratio, the square root of the ratio, because I was thinking of times or something like that, because I wasn't thinking clearly, because I've been at this for about 3 hours so far. And there's no excuse if that was wrong. But work it out yourself. See what you get. See what the ratio ought to be. Maybe it's a square root of 0.67, which would be about 0.81. And maybe it's just plain old 0.67, 2/3 the acceleration of gravity, about 6.5 or 6.6 meters per second squared. And of course, that factor 0.67 or 0.815 or whatever it is would go in front of G sine theta. Okay, goes in front of this, just doesn't go in front of G. But as far as the operations that you do, you could just put it in front of G. I'd like to change that to 1.33 or 0.8, 1.6, whatever. Okay, that's enough.